1.4 or 1.3, sorry, 1.3 transformation of functions. So transformation, right? Any function can move up, down, left, right, and they can stretch or shrink, and we'll talk about this. This is horizontal and vertical shifts, right? If we have some function and we add a value at the end, like say x squared, if this is x squared, and we add something that's going to move our normal parabola for x squared, it's going to move it up too, right? If we subtract, it's going to move it down. If we take a number minus our x, so if I pick some x, say on an x squared, well, the function might not be x squared yet, but if before I square it, if I subtract some number from that before I square and then I square, that's going to move my graph to the right c amount. And then if I add before I take the function, that's what basically said you're doing the action before you complete the function. So you pick some kind of x, you minus it or add it, and that's going to make your function move left or right. So if I subtract some number from it, it's going to move to the right. If I add some number, it's going to move to the left. Because basically, you're not necessarily changing your x, but you pick your x, and then because you're adding or subtracting, it kind of changes that value before you do the function, whether squared or cubed or rooted or whatever. So these are the kind of the shifts in graph. We can go up, down, left, and right. So those are vertical and horizontal shifts. And then we have reflections, vertical stretching and shrinking, and reflections. So if I have some type of function like x squared and I multiply it by something, that's going to stretch the graph vertically by whatever that number is out in front, right? If I multiply it by a fraction, which is really dividing by that function, then it's going to shrink it vertically, right? And if I multiply a number before I take it, so if I multiply x before I take the function, like a squared, that's going to shrink it horizontally. So really it's going to kind of compress it. So it's going to make it kind of, for our example here, say that's the normal x squared. If I multiply it by 2 first, and that's just going to make it a little more, it's narrower. So it's going to shrink it, but it's going to shrink it vertically. So it's kind of compressing that function. If we divide by a number, so I times by 1/2, and then I square it, that's going to stretch it out. That's going to stretch it horizontally. Okay. And then if I take my function and I multiply it by a negative, that's going to flip it about the x-axis, because that's really, that negative just means opposite of my function, so it's going to flip it over x. If I take the negative before the function, then it's going to flip it over y, right? So I can have negative x squared, or I could have negative x, and that quantity is being squared. So this one would flip it over the x-axis, this one would flip it over y, but it's a squared, so that one really doesn't matter. But if it was like a cubic or something, then it would change, or root. So that's the reflections there, and then vertical and horizontal stretching and shrinking. So same thing when we talk about trig functions. Trig functions can stretch or shrink. You know, if we multiply by something, multiply by the trig function a number of times, the trig function is going to stretch it vertically. If we divide, which is multiplying, right, by a fraction, that's gonna shrink it horizontally. And then if we do it on the inside, right, if we do it on the inside, that's going to shrink it horizontally. And if we, where's the other one? I guess this one up top, sorry. I guess I'm not kind of drawing. So here on the outside, it's going to stretch it vertically. If it's multiplying by a fraction, it's going to shrink it vertically. And then if it's on the inside, if it's a fraction, it's going to stretch it horizontally. And then if it's also on the inside and it's a multiple, bigger number, then it's going to shrink it horizontally. So kind of like shrinking horizontally is very similar to stretching vertically. Vertical stretch. Because if you look at this one, and on the inside, let's see. So my numbers well, maybe trig functions not the best example because we only go so high. But those are kind of similar when we do like x squareds and stuff like that. But they're not necessarily equivalent, right? Because one with this one, it's pretty good because if I stretch it vertically, it's going to look something like stretched out like that, which is very similar to pushing, shrinking horizontally. So they're kind of similar, but not really exactly the same. Okay, so these examples, here's our main function that we're doing. So this is f of x. And so here, this is taking f of x and subtracting 2 from, so that's going to go down by 2. This one is subtracting 2 before we take the function, so that one is going to move to the right 2. This one is taking a negative on the outside of the function, so this is f of x and then to the negative, so that's going to flip over x-axis or reflect over x. This one's multiplying by 2, so it's going to stretch it vertically by 2. And then this one, I'm taking the negative on the inside, and so that's f minus x of x. And so that is going to flip it over y. Combination of functions, this is something that we've done before when we have two different functions, f function and g function, and we're adding them, so we can write it in this form, f plus g of x, or f of x plus g of x. So that's adding functions. We just combine like terms. These ones are not like terms, so we just leave it just like that. And then we have minus. You got to be careful on the minus because basically you got to distribute that negative, and then you can combine like terms. And again, these are not like terms, so it's just f of x minus g of x. But make sure on the subtract one you distribute that negative. So the last one is adding and subtracting. This one's multiplying, so f times g of x, or f of x times g of x, like that, or division, f divided by g of x, or f of x divided by g of x, where g of x cannot equal 0 because I can't divide by 0. Oops. G of x cannot equal 0. And so here are some examples. Here's our f of x, here's our g of x. Multiplication is pretty straightforward. Most of the time we're just distributing. All right, so we take f of x and distribute that into our g of x, and so we get x cubed minus x squared. Division sometimes can be, sometimes it can be easier and sometimes it can be harder. This one's not too bad because we can't really reduce that because this is subtracting here, so we can't cancel those x's or anything, but we want to state our domain. So this is just going to stay the same, but we want to state our domain. X cannot be 1, right? So that can be everything but 1, but not equal to 1. Okay, so on those division ones, you just want to state your domain. And then what you would normally do on some of these, you might try to factor, but I can't factor anything out of this denominator. So you try to factor and then cancel like terms. And the last one, we have combination of functions. So combination of functions is like f of g of x. So f of g of g. So f of g of x, or f of g of x. It could be looking those two different ways. So it is plugging g into f, because remember f of 2 means I'm plugging 2 in for x. Right, so if I have f of x equals, say, 2x, f of 2 would be plugging in 2 in for x, so this would be 4, right? Well, if I have g of f of, or sorry, if I have f of g of x, means I'm taking g of x and I'm plugging it in for my x on the f equation. So it goes inside out. So I take g of x and I'm plugging that in for this x right there. So that square root's going to stay the same. That x is now going to become x squared plus 1. And then I can try to simplify this one. You can't simplify because there's addition here. So remember, square root means something times itself. So if it was this squared, square rooted, then yes, my answer would be x squared plus 1. But this is not being squared, so it's not going to equal that. So remember, composition of functions is putting the inside one into the outside one. So here's kind of an illustration from the book. F of g of x is taking, you got your function, you got your x, you're plugging it into your g equation, and then you're taking that answer of your g equation and plugging it into f for x to get your answer. So when you have, like, say, if I would have f of g of 2, what that equals, that means I'm plugging 2 in for my x equation here. So that'd be 4 plus 1 is 5. And then taking that answer and plugging it into f, 5 into that would be square root of 5. So that's kind of the diagram here is kind of showing. So here's another example. So this is threefold. So this is f of g of h of x. Or it can look like that. So I'm going inside out. So I'm going to take h, plug it into g, and take that answer and plug it into f. So I'm going to take g, which is, let me decipher this g right here. I guess it's not going to move for me. This g goes right here. And so I'm going to take h, which is cosine of x, and I'm going to plug it in for the x of g, which is right here. So I'm going to square this g. So I'm going to square cosine. And then I'm going to add 1. And then I'm going to take that answer. I'm going to take that answer. And I want to plug it in for x of this x right here. So that's where we get square root of cosine squared x plus 1. Again, I can't cancel anything there because I would need this binomial being squared, which it isn't. So, which it's not. Okay, so that's it for that. Under 12 minutes.